Thanks for that, David. That was really interesting. I'm also talking about my PhD. So for those that don't know me, I am currently working at the Coal Authority as a research and development manager. I started there in November, but today I've got my PhD hat on. So I'm talking about some of my results from my PhD, which I recently handed in. So there's a picture of me just doing nice temperature probes in a shaft, just in case you've never really seen me. And don't worry, I'm not going to try and put my whole PhD into this 10-minute talk. I've got some heavily summarised information for you. So that's the title of my PhD, was modelling the thermal, hydraulic and mechanical controlling processes on the stability of shallow mine water heat systems. And I'd just like to say that I want to thank my supervisors, Chris, Gus and Stuart from Edinburgh Uni and Alex Bond from Contessa for helping me through my PhD. It was a long old process. So what am I looking at? Well, I mean, I'm sure you've seen this map before. This is the map of the large cities underlain by mine workings. And one thing that there's been limited research on kind of geomechanical impacts of storing and removing heat from these systems. So that's looking at how does the heat interact with any of the rocks and what happens to the mining systems if you take the heat in and out of the system. Now, what I've done is I've created a thermal, hydraulic and mechanical model to try and get an understanding of some of these processes. And I've focused on the shallow pillar and stall mines. And this is because they are likely to be kind of most likely to potentially fail. And also they're the shallowest generally systems, which are of most interest if we're talking about kind of surface impacts. So I'll go through my model and some of my results. And yeah, hopefully there'll be some questions at the end. So I just wanted to show here, because not a lot of people, not everyone's seen kind of pillar and stall workings. And really these are pillar and stall workings where these pillars kept the top of the mines from collapsing on top of the miners. And what happens is they've kind of been left in place. And so what I'm looking at is how does taking heat and in and out of a system, does it impact these pillars at all, which have been left in place? So in terms of my model setup then, I focused on one layer of shallow workings. And this was because I had to make quite a simple model for all the calculations. So I focused on 5 pillars here, and I made the pillar and room sizes. I used quite a lot of different indices to come up with kind of reasonable sizes of these, and I can go into more detail on that if you need. And I worked with the workings at 61 meters depth. And the reason for this is I wanted to have, I needed to have a fairly saturated model, and I wanted to have enough space above my model to allow water level to change. But I also didn't want my workings to be too deep, because otherwise they wouldn't be representative of shallow mine workings. So that's kind of my model setup. In terms of my how I added in the boundary conditions and everything, what I did was I added on an overburden, so a vertical load above my model to represent the overburden that I didn't include in the model. I then made the water level a metre above the top of the model, and this is, like I said, I wanted to keep it fairly saturated. I gave a thermal gradient of about 3 degrees per kilometre, which is a kind of standard geothermal gradient for the UK. But I added a thermal flux at the top and bottom so that it was going up. So it was coming in here and going out the top of 9 to 8 milliwatts per metre squared. And the way I injected and abstracted heat into my model was I assumed that this is a quarter. So I assumed that there'd be an injection, say, at this point. But instead of kind of, as a worst case scenario, I worked out that you would inject heat and it would kind of go and connect to all these stalls in one go. Obviously, this is a 2D model, and so your heat isn't going to get through to your whole model in 2D. So what I did was I added in the heat, injected the temperature on each of the stalls to kind of have a standard temperature across the workings. Obviously, in 3D, if you injected heat here, it wouldn't be the same temperature over here. But this is what I worked at as a kind of assumption in my model. And one of the main things I looked at was how do we assess when the rocks are kind of towards failure? So what am I going to use as my failure model for the system? So how do we assess the stability of the mine workings? So what I worked on was a factor of safety analysis, and this is a standard kind of engineering thing where you look at the resisting forces and the disturbing forces, and you look at the factoring between them, the ratio between them. And I'm not going to go into all my calculations. I know there was lots of calculations yesterday, but it's too early on a Thursday morning to go into them. But if you're interested, I can go through it with you. And I'm hoping to publish my work, so hopefully it'll be in the public domain soon. But basically, I worked on a factor of safety less than 1. So above 1, it means that the material is probably stable, and below 1, it means the material is likely to have failed. Now, I'm not saying that this is an absolute value. I'm just using this as a kind of criteria to assess my models. So here's some results then. What you can see here on the left-hand image is my first step. So I did my model for 20 years, and there was there were kind of 6 monthly cycles of injection of heat within that. And so in my step 1 here, you're injecting heat into these stalls here in between the pillars. And then by the last step, the second last step, where you're still injecting heat at 50 degrees, you can see the heat is moved throughout the model, and it's heated up the whole model. And before I go on to specific results, this is an image of my model with the mesh and kind of my output points. And for today's talk, I'm going to focus on these four points here, A, B, C, and D. And if you look, so point A and B are above the workings, they're 5 meters above the workings, and C and D are below the workings. And A and D are above and below a stall, and B and C are above and below a pillar. And this is just to try and get a comparison of the impact on these points. So what you can see here, now this is factor of safety, my calculated factor of safety over time at those 4 points that I was talking about. And what you can see, the first thing to look at is that initially there's these really high values, and it comes right down. It starts up really, really high, and it comes down. And the reason for this is that because of the way that I had to model, I had to have a kind of initial step in to provide initial conditions for the mechanical solutions, which uses ambient temperature. And that means there's very little shear stress, which gives me very high factor of safety values. So we're not going to talk about them further just now. But what you can see is that there's a cyclical pattern to the results. So each point has this lowest factor of safety, which means it's closest to failure at the end of these heat injection cycles, which are shown in pink. And the next thing to notice is that above the stall, so that's A and above the stall is figure A. Here, this blue line, and that's the one that's closest to failure, whereas the one that's below the stall, below the pillar, is furthest from failure. And so that shows that there's a kind of spatial impact to a spatial element to the results, and the element and the around the stalls is probably going to be more likely to fail than around the pillars. And what this is driven by, well, this is driven by if you look at the differential stress, this is the change between the maximum and the minimum stress. And if you see here, that's shown in red dashed, and that's showing the same pattern, the alternative pattern to the factor of safety, which indicates that this is what's driving the change in factor of safety. And this is driven by changes in temperature, pressure, and displacement in the model. So this is, as I was saying, this is differential stress. This is maximum stress, taking like the difference between the maximum and the minimum stress. And it's a kind of proxy for factor of safety. So where you've got the highest differential stress, you've got your lowest factor of safety and you're closest to failure. And what you can see here at an injection temperature point, so this is my second last step where I'm injecting 50 degrees into the model, you've got these high areas of differential stress around your workings. And this means that this will be the closest part to failure. And then when you're not injecting heat, you kind of got a lower value, so you're higher and you're more stable. I did lots of assessment. Obviously, I'm not going to go into full details about it, but just to go through a few things. I changed various parameters to see what would actually impact the results. And what I found was that heat injection has the largest impact on the factor of safety. So if you look at this figure down here, these are 3 models I did where I had heat injection in the model. I also just had a model which had water level change only, and I had a model which had water level and heat injection. And if you look at it kind of zoomed out, you'll see that this dashed green line, which doesn't have any heat injection, that's much more stable than when you had the heat injection in. So as soon as you add heat into the model, it reduces the factor of safety dramatically and brings it much closer to the threshold. The next thing to look at is the injection temperature. So if you look over here, the injection temperature does change with the factor of safety more than, say, the overburden properties does, or the room properties. So the injection temperature that we've got is of more importance than, say, the overburden. Now, obviously, I've been talking about bringing the system closer to failure, and I've been looking at homogeneous isotropic media, which is not the case in a model. So what I want in real life. So what I wanted to kind of show is that when these mine workings are going to have kind of some sort of damage zone around the workings, which is going to have faults and fractures and different rock materials. So what's the impact of adding a zone around these the workings? So what I did was I kind of created a zone around, and I changed the permeability and thermal conductivity and the Young's modulus. Now, it's obviously difficult to know what the parameters are for that. So what I found was that if you look at the point A and B, where you've got your base model in blue, if you add this damage zone around your workings, the factor of safety is more stable, basically. So what's doing is that this zone of damage is diffusing the shear stresses, and it's making the system more stable. So what I wanted to show is that although I'm showing that they could be close to failure, it's very dependent on what's happening in the damage zone around the system. So in conclusion then, what I wanted to show was that my results are obviously the first time that anyone's really sort of looked at the hydromechanical impacts of these systems, and what it can be used as a comparative purpose only. I'm not trying to say these systems are going to fail if you start using injecting and abstracting heat. But what it does show is that cyclical injection and extraction does impact the system stability. So there is an impact on it. And this is spatially important. So close to the workings, there's more of an impact. Geological layering is important. So the stresses kind of build up in the harder rocks, but where you've got these softer rocks in this kind of damage zone, there's lower stresses, which makes it more stable. And there could be operational consents. So for example, the things that you can control, so the injection temperatures and the water level changes, they've got more of an impact on the stability than the underlying geology, and so that could potentially be used in some sort of regulatory system to try and look at it. So yeah, that's me finished. Thank you.